Okay, so now we're looking at related rates part 2. We're going to do a couple more examples from the textbook, from the Cengage Pearson book, to cover related rates. So example 3 says a water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, so we're talking about a relation between the level of the water, the height, and the radius of the cone, which is 2 meters. So let's consider the shape of our tank here. If I can draw a decent cone, we'll see. It's not bad. Okay. And it's definitely not to scale. Let's see, the radius here is 2 meters. And the height here is 4 meters. Okay. And we want to look at when the water is 3 meters deep. Okay. And what we know so far, okay, water is being pumped into the tank at a rate of 2 meters cubed per minute. Notice that we're talking there about volume. dV dt equals 2 meters cubed per minute. And what we want to know is, what is the rate at which the water level is rising? What is dH dt? Okay. So we want to consider an equation, okay, a chain rule type equation that relates the volume and the height and the time. So remember, based on our chain rule, dV dt equals dV dH times dH dt. Okay, so one of those we know dV dt. We need dV dH. Now here's the tricky part. The tricky part is that we need a formula for the volume of a cone that only has the height in it. I mean, we could mess with the radius. We could try to integrate it in there somewhere. But what we're going to do is we're going to set up some ratios that help us to eliminate radius as a variable in this cone. So typically we know that the volume of a cone is 1/3 radius squared times the height. Okay. That's the typical formula. Oh, I forgot a pi. Always got to have a pi in there. So we got pi r squared for the area of the base times the height. That would give us a cylinder. Then we multiply by 1/3 to get a cone. So typically this is where we'd start for the volume of a circular cone. But what we want to do is relate the radius to the height. Now, what we notice is no matter where we go in this cone, we always have similar triangles. And so the ratio of the radius to the height is always going to be the same. It's going to be the same at the top of the cone as it is halfway down the cone, and so on. And the radius is always the same at the top, like I said, 2 meters to 4 meters. Okay? So, in other words, the radius is equal to half the height. So what we can do is we can substitute that into our volume equation. To eliminate that radius as a variable. All right. So now we've got a brand new volume equation. So let's take that to the next page. Volume equals pi over 12 h cubed. Okay, so now we can use this to find dV dH. dV dH would be equal to pi over 4 when we multiply that 3 down, okay, times h squared. All right. Now, going back, we said that dV dt is equal to dV dH times dH dt. So let's start substituting stuff in. We said dV dt was 2. we said dV/dH is pi over 4 times h squared. And what we're interested in is dH/dt. When h is 3 meters. So if we plug that in and do some basic simplification, okay, we're going to get 8 divided by 9 pi, which we can do it on our calculator, and we find it's approximately 0.28. So what's our units? Well, our height is measured in minutes, and the time units we've been using, our height is measured in meters. The time units we've been using are minutes. So this tells us that when the height of the water in the tank is at 3 meters, it's changing at a rate of 0.28 meters per minute. Okay, that's how fast it's rising. And we know it's rising because, first of all, it's positive, but water is going into the tank. So basic logic tells us that the height of the water is rising. All right, let's look at example 4. This is a twist on a problem that often gets made fun of, where you got train A leaving one station and train B leaving the other section, or the other station, and when do they run into each other? So we're going to look at it in kind of a similar fashion. We've got 2 cars approaching an intersection. Now we've got car A traveling west. So first of all, let's draw our intersection. Let's call it here. All right. And we've got car A traveling west. And we've got car B traveling north. Now, car A is traveling west at 50 miles an hour. Car B is traveling north at 60 miles an hour. Both are headed for the same intersection of the 2 roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Okay, so let's take this in a little more detail. Let's look at it on a coordinate axis. Okay. Let's suppose car A is somewhere around here. Okay, don't worry about the units at this point because we don't really know. Okay, and we've got directions for them as well. Okay, now we've got an x value here. Okay. We've got a y value here. But what we want to know is, how far apart the cars are. Okay, so the question asks, at what rate are the cars approaching each other? Okay, so that's the distance between the 2 cars. So if we connect those 2 points, okay, connect the 2 cars, let's call that z for now. Now, we know that z squared equals x squared plus y squared, okay? And we want to know how fast the cars are approaching each other. So I'm going to use an abbreviation here I used a lot in college in proofs. We wish to find, or we want to know, so you can use K, however you look at whatever you want to write, what dz dt is. Okay? Now, what we need to remember, well, let's set up our equation here first of all. If we use implicit differentiation and take the derivative with respect to time of each of these, we get this basic equation. Okay? And if we divide the whole equation, if we solve this for dz dt, which is what we're trying to find, we find dz dt equals x over z dx dt plus y over z dy dt. Now we know that at the time we're looking at this, car A is 0.3 miles from the intersection, car B is 0.4 miles from the intersection. So we're talking about a point at when x is 0.3 and y is 0.4. If we go back to our equation, x squared plus y squared equals z squared, and substitute those in, we'll find that z is equal to 0.5. Okay, so now we can take this equation a little bit further. dz dt equals 0.3 over 0.5. dx dt plus 0.4 over 0.5 dy dt. So the question is, how is x and y changing with respect to time? Well, the change in x with respect to time is its speed. The change in y with respect to time is its speed. So this is the speed of car A. This is the speed of car B. Now, what we want to remember is that these two are actually getting closer to each other. The distance is decreasing. So we don't want to use the positive value of the speed because that's going to take us in the opposite direction. It's going to mean that the distance between them increases, and we want it to decrease. So we're going to use the negative values to show that they're getting closer together. So dz dt is 0.3 over 0.5 times negative 50. And 0.4 over 0.5 times negative 60 as they move closer together. Simplifying this gives us, just having a little technical issue there, negative 30 minus 48, which gives us a rate that they're approaching each other of 78 miles per hour. Okay. Again, that negative shows that the distance between them, that z, is decreasing. All right, so there's 2 questions on related rates and the examples from the book. I hope this helped.